In the document. Give me. Yeah. I mean, palm is from. Okay, okay, we can start. Uh, yeah, 19. Yeah, it's like in simple document. Yeah, but it's only 1 hour, so we have 1 hour for preparation. Maybe we can decide. Like, okay, talk later. All right. So we will start the final lecture now. So today is the final lecture, and we, I and Carlos, will summarize what we learned in more than 20 lecture. Yeah, so it would be a lot of topic. Yeah, they are all interesting, all important, but we only focus on some topic fundamental, basics of every state-of-the-art model now, and also the topic you should focus most because it will be relevant to the final exam, more relevant to the final exam. So and the exam that you know is in the 31 August, and we have 3 lecture hall. When the exam will take place in a 3 lecture hall, and it's around 60 minutes, and you are not allowed to use any tool like calculator, or you are allowed to use only pen and paper, and you have a 6 point bonus totally through your assignment. Yeah. I already mentioned this before. Oh yeah. So the bonus point only apply if you pass the exam. So yeah, I mean you have to pass, and the bonus point will apply later. And so the basic thing is will be the supervised learning, the unsupervised learning, the activation function, the underfitting, overfitting generalization, the inductive bias architecture, the regularization method, and the loss function. So what is a supervised learning? Supervised learning is something like you have a data and the label, and you have trained the model to learn how to map the data with the label. And like example here. Um, so we, we have a label for the data, and the model will learn how to classify the data. Um, it's not only the classification problem. It's maybe the regression problem, like you can predict the price, you can predict the degree of the day. It's not only the classification problem. So it is some it's about supervised learning. Okay. The second topic is about unsupervised learning. In this topic, we learn about how to, clustering, how to learn something, represent something from the data we don't know the label. Like in the lab figure, you learn about how to cluster the data. How many clusters should be best for this data, and in the right figure, you learn about the auto encoder. That means you learn to know how to present the data without the label. Like you will have something like hidden representation of the data, and this hidden is much smaller than the data, and it's we can consider it's a kind of the compression. And this hidden, of course, is present for the data. So you can learn something like you can use this hidden representation for clustering. You can use this hidden representation for classify something. Like if too hidden, it's too far away, so it should be class, for example. Yeah. So next topic is about the activation function. So here we learn, yeah, the neural network is impossible to train a neural network with only the linear function because it's if the neural network is everything is linear, so it's the deeper it's not no, it doesn't matter because all linear is combined. The combination of the all linear function is only the linear function. So it needs so so it requires some non-linear activation function. For example, like a sigma function. We use sigma function for classification. Uh, you know, when the input is range from uh, infinitive in the range of infinitive, so it can be output the output the value between 0 and 1. And the sum function is very popular for the multiple class classification. So we will learn how to generate the distribution with the input, with the logic input. Yeah. And the sum function is um, com commonly applied on the last layer. You know, you have to classify which class the input belong, and the last activation function we learn in the pros is the value function or rectify linear unit. I mean, you basically it's apply a linear function, but if the value below is 0, so it can be 0. So yeah, so all the activation function has their own purpose. So yeah, and the value we have a better radiation because the the derivative of the value is 1 if the value if the input higher than 1 and if 0 if the input lower than 0. So it makes the network learn faster with yeah. And the sum function is help the network the classify and to convert the output the input to the probability distribution. And the next very important term is the loss function. So the loss function is the way we evaluate the model, and it's the way we need to optimize. So so if we have a loss function, we can use some optimization method to to, to train the model and to minimize the loss function. So they some famous loss function like loss entropy loss with apply when we use the sum function at the last layer. The, the mean square error or mean absolute error. So we apply when we are then we are training the model to do some regression problem. And the binary cross entropy loss, yeah, we can apply it when we train the binary classification uh, and uh, and also for the binary cross entropy, so it's binary classification, so it can apply on if you use the sigmoid at the last layer or even the format at the last layer. So so the next term is the generalization. generalization. So then generalization that means we evaluate how good the model learn when it apply on the test data. So there's some term like overfitting that model learn quite well in on a training data, but it doesn't learn well on the test data. So it's called overfitting. So that we need to prevent. Yeah, the underfitting that means model is not learn well on the train data. That means the accuracy or the loss function in the train data is still very high. Yeah. And we need to know the integration of the learning curve. I mean, we know when it's overfitting happen and when underfitting happen, and we need to know several ways to prevent overfitting and underfitting. Like to prevent overfitting, we need some kind of utilization method like dropout. Dropout is something like we run them drop the weight, the output of the network to make it to be to so make it zero. So if the model would not focus on some very specific node, and it needs to focus on more on the other node, so it makes the generalization better. Yeah, of course there are so a lot of other regularization methods like local smoothing, like some normalization technique also very good method for regularization. Yeah, so next we talk about some inductive bias. So I mean some architecture will bias on some specific problem like RNN with a sequential bias and locality bias, so it's very suitable for some sequence problem. And CNN, the convolutional neural network, is very suitable for some computer vision problem because it has partial bias. I mean, it has very small kernel and it's applied on very small part of the image, but it's very useful for the image classification or computer vision problem because it it can learn the can share the parameter and it can learn some local information, which is very meaningful for the model can classify the image. And also the SIP invariance, SIP invariance or SIP equivalence also. And the the most superior architecture now is a transformer. It has a it's combined it has a global attention or global information, and also it has a directionality. So it has some it's good on it's good for both the NLP uh, computer vision problem, and also some NLP problem like tokenization. Yeah. So in the exercise, we can ask you to calculate something like forward path of the network, like you provide the weight, you provide the input, and you with a simple neural network or CNN or INN, you need to compute the output of the network in the forward path, and also you can ask you to do the backward path. I mean, we give the network, we give the input, and you calculate the output path and the, the derivation of the every weight of the network and also derivation of every output of the layer of every layer. Yeah, and a simple neural network, or we can call it a fit for work like fit for work neural network or multi-layer perceptron. And maybe you are familiar with this type of network because we already mentioned it on the first exercise. So The neural network is process input and produce output on X node of the network, and that you so and the output layer will represent the class 4 of the number, or maybe the relation. Yeah, yeah. On a few familiar with this architecture, uh, if you try to implement the exercise. Then, so in the lecture 5, we learned about the TDM and CNN. So the TDM if you can consider it the first CNN before the CACN term is invented, because actually it's a 1D CNN, so it's applied on the sequence program on the time series data. And and it also has some feature of the CNN like shift variance, local bias, and it's the first neural network to apply on speech recognition. And of course, the CNN is a very famous architecture, and it's very successful apply on image and classic character recognition. So next I will give the stage to Carlos to talk about the vanilla. So he can talk about the recovery network and the transformer architecture.
Okay. I guess I'll take it from here then. Okay. Mm-hmm. How do you do this? I need a second. Okay. Think wrong. Okay. Yeah. So maybe I have a few comments on the slide so far. Wait. So first of all, there were two questions in Ilya. First question was whether the students are allowed to use the dictionary, and what's the exam language. And there's been some experiences from my past colleagues. I think in the past there has been some trouble when they have a bilingual exam. So if they have the questions in German as well as in English, there was some problem. I have to ask what exactly it was. But I think in the previous years it was usually in English as well as in German, right? So I think probably it will be in English as well as in German. And you will get both. With the English version as well as the German version, you can choose one. So I think you might not need a dictionary. Do we allow dictionaries? I think maybe not. I mean, I will consult with maybe I don't know, but maybe it might be better without allowing dictionaries. I mean, if you get an English as well as the German version, is it necessary? Does someone still want a dictionary? Anyway. And yeah, and the presentation slides for the current lecture will be available there. Yes, we will upload them. About these numbers up here, the lecture 10. Actually, I'm not sure whether all of them are correct, guys, because I think some of the lectures might have been in cognitive system, right? In the cognitive system videos. I think at least some of the clustering methods and such were in the cognitive system videos, right? Mhm. But I was wondering, some of the um, basics like this, was it not in cognitive system? Anyway, but all the stuff which is here on the slide, which we're showing right now, it's relevant for the exam. So whether it's in our actual slides or in the cognitive image background, what you find here on the slide is definitely relevant. Yes. Do you want to say something? Yeah. But any of the stuff we showed so far, was it in the background? I'm going to use it again. Yeah, anyway. Um, yes. So one question I was also asked before is whether in the exam you will have to, well, compute by hand or calculate stuff by hand a lot. And I I personally think we won't. I mean, I personally will maybe not design. I mean, I'm not making no promises, but um, I personally prefer these sorts of tests where you don't have to compute stuff by hand a lot with numbers, but you will definitely have to know how to do symbolic differentiation of, I mean, do the backwards pass symbolically, and you should easily be able to do stuff like symbolically differentiated NLP with respect to the input as well as the weight. Um, Anything like that? Yeah. Okay. Then about the RNNs. Yeah, in the lecture we also looked at RNNs. We first looked at vanilla RNNs. And those are just type of neural network which we can use to process sequences of vectors. And they are always, we have a state, a hidden state. And we produce a new hidden state, taking the next vector in our input sequence, and producing from that the new hidden state as well as the new output in our sequence processing. And there's in its simplest form, it's just a concatenation of the hidden state and the new input, a matrix multiplication on that concatenated vector, and then a non-linearity, and another matrix multiplication to get the I remember to get the vector thing. We also looked at some advanced types of RNNs, mainly at LSTMs, and we also especially looked at how to train those RNNs. We should also know about the vector propagation through time. For its the different types of vector propagation through time, we looked at different kinds of tasks. So, for example, sequence labeling, like for example, sentiment analysis, where we have a single label for the whole sequence, or sequence like no, that's sequence classification, I mean. And then we also have sequence labeling tasks where for each input we compute one label. For example, let's say an example for that would be part of speech tagging, where you for each token in the input sequence compute whether it's, for example, noun, verb, and stuff like that. And depending on what kind of task we have, the loss function looks a bit different. Yeah, and of course you should also know about the different types of tasks in general. Like for a given task, you should know what kind of network we would best apply to it. And given, for example, a certain type of task which we describe in words, you should be able to understand whether it's a sequence labeling task or whatever. Also in sequence processing, we have the transformers. Transformers are, of course, very important. And you should actually know them in detail. So first you should know what transformer layer is composed of. So these four components, which are the multi-head attention, the multi-layer perceptron, and in between them, of course, the residual connections, they are also important. And then maybe also remember there's a layer one. And besides the layers themselves, you also have to know, of course, that the self-attention or attention in general is not position aware. So since it's just since basically the attention down here is a we have a quadratic number of dot products of different vectors. We don't really have any position awareness of which vector is being multiplied with which other vector in this attention formula. So we need some form of input position representation. Yeah, and for this we have this input, the position encoding formula. And you should definitely know about this one. And I think, will we be talking about the second exercise later? Yeah. So the second exercise will also be announced later, and it will also be about transformers, and there will also be an extension of the exercise talking about position and coordinates. Sorry, for the groups, I mean we. Okay. Oh, really? But in the first one, we didn't allow groups yet. Oh, okay. Oh, okay. Okay. So yeah, in the first one, in the first exercise, we didn't allow groups, but in the second one, we will allow groups up to 3 people. Okay. Yes. So you should definitely know about the position importance because they're quite important to get some information to the self-attention of which positions are being looked at. Right. And of course, you should also know about input embeddings, but these input embeddings you should know about independently of transformers. They're very important, independent of transformers in general and sequence processing. I'll talk about them later as well. Yeah. Okay, and then also finally in sequence processing we talked about these state space models, which is another type of RNN, which is more suitable for long range sequence processing than the vanilla RNNs or the LSTMs, due to the nature of the map. And basically, what I can say is that we can control through this so basically through the diagonalization of the matrix A, which we so it's basically like a you can imagine it like a vanilla RNN, but without the nonlinearity in the time axis. And by leaving away this nonlinearity in the time axis, so in the layer axis we still have nonlinearities like in the transformer, but in the time axis we leave them away. And by doing that, we can control vanishing gradient problem. And what we can also do is this matrix A over here, which is multiplied into the state, like it's being done in the vanilla RNN. That one can be diagonalized, and then if it's a complex matrix, we can control this vanishing of the gradient by controlling the no, by making sure that the um, matrix is within the with a complex unit circle, and yeah, go look at these slides on that part. Um, right. Um, what else? What we also talked about is, of course, the representation of words, let's say sentences in natural language in neural networks. And since we need to some way to vectorize um, the sequence of words, we will learn word representation and then look up the word that appears during the forward class for the given words. But since if we do that naively, we get a huge vocabulary. We do a thing called subwording. And one special case of subwording is bytecode encoding, where we apply the sort of compression algorithm to word sequences to split the words into smaller words. And then we get a fixed amount of possible words in total, and that's a smaller vocabulary. And what you should definitely know, I mean, what we had was one research lecture on neural learning, right? And my colleague Kristen, he talked about how we can represent, I mean, first of all, whether it's possible for transformer or sequence modeling neural network to represent new words. And with BPE, the answer is yes. I mean, if we have some word which was never seen in training, in the worst case, we can split it down to the single characters in the word, and those will basically guaranteedly be in our BPE vocabulary. And that way we can represent any sequence of unknown words in our transformer. But there's still some ways to improve the processing of unknown words. Yeah. And you should be aware of this whole problem of whether or not we can represent new words, unseen words in using, for example, transformers. Here, the slide explains how exactly BPE works. In my opinion, you maybe don't have to be so much aware of how in detail the BPE algorithm works, but more about the application and how it affects, well, the neural network part. Yes. Then, of course, one very important task, which we looked at, is language modeling. You should definitely know about language modeling. You should know, of course, what language modeling, I mean, what is being modeled in language modeling, so this probability formula. And yeah, of course, you should know that this whole training objective is the next token prediction. And what we also looked at was in the context of machine translation, this decoding algorithm called beam search, where we basically during we finding, I mean, the model, the neural network has, for example, a language model, has the ability to assign probabilities to a sequence, right? But then when we want to generate a sequence, then we need to first find those sequences to assign the probability scores to. And this generation of the sequences is called decoding. And one type of decoding is, well, for example, sampling, where we just sample from the output distribution, always one token. And this is usually being done in language modeling. But in machine translation, what is better than sampling is beam search, where we just basically cover a larger part of the hypothesis space. And yeah, this hypothesis space was the space which is exponentially large. Yeah. Anything else so far? You want to? Okay.
So I will continue with the topic image classification. Yeah, image classification, yeah, means you train the model can classify the image. So before the CNN is invented, we use the linear classification. That means we convert the image with a 3D image like uh, 32 and 32 and 3 to the sequence of the pixel and input it to the feedforward network. And in the last layer, it's a sum function, and you can get the actual probability distribution of the image as before the CNN was invented. But but when we have a convolutional neural network, so it trained the trend of the image classification. Is a convolutional network is consists of a lot of convolutional layers, which have a kernel, small part of kernel like pi and pi or three and three kernel, and it focus on every small part of the image, and it will be output the feature map. So it's been very suitable for the image classification, as you know, and X X point of X X X pixel of the feature map will have the receptive field. That means how many pixels it will be represented in the original image. So like in the second figure, we use the phi and phi kernel. So the the receptive field of the one pixel in the pixel map output it would be the pixel in the original image or phi and phi in the original image. So if we add more and more convolutional layer, so the the size of the receptive field will be increased. So that means one pixel in the picture map has more and more meaning. If we go more deep, then once we can increase the size of the receptive field is the max pooling. That means we choose the max value of the small part of future map. So like in the third figure, each pixel here will have uh, two and two receptive field in the original future map. So it will be increase the receptive field more faster. So yeah, so that's why. So but so we can don't need the big convolutional network because the convolutional network can save a lot of parameter and also very soon for the unit classification. Um, and we can apply a transfer learning on convolutional network by we train the model on very big corpus. We have like image net corpus. We have a lot of class, a lot of image, and when we have this, so this model will have very good representation for the image, and we can type in this model on the downstream task line. We have a small task line here, face recognition, only the class is different to the it's not similar to the image, but we can use the keychain from the image to Python on, for example, face recognition. So, if we apply, if we use the transfer learning, so we can set, the uh, training time. We can, we can do a doesn't need much training data for specific tasks. And when we represent or we solve every future map of the neural network, you can see there's a lot of representation in you can see in the figure, fixed figure. So in the very first layer of convolutional network, so it's a low level feature, so it's still similar to the original image. It's, and it will go more, it will go deeper, so it's more abstract. It's a high level feature. So it's not look like the original image, but it has more abstract information about the image. So it can have the last layer, I mean the linear layer. The last linear layer easy to classify the input. Yep. And so it's just how we apply the convolutional network on image classification. Or even there is the other problem like object detection, object segmentation. Also, we can apply convolutional on this kind of problem. Next, we talk about the generative model. Uh, we have learned uh, maybe a three types of generative model like the version autoencoder, the game, and the diffusion. But we should focus on more the first type of architecture because it's more, yeah, it's easy to, I think it's not complicated as a diffusion, and we can, we can, we can, we can easily to write code or implement it. So first it's about the various model. So generative model is the first of generative model is if a trained model can learn the big issues in the data, or can learn how to generate the data. So if we can learn the distribution data, or we can we can sampling a new data from the from this distribution. So in the version of autoencoder, uh, in the conventional autoencoder, that is the only the vector. But in the version of autoencoder, that is the sample from the two prior distribution. So so it's also sample from the true conditional distribution. Conditional distribution here is given by the latent depth. So so to train the version of the encoder, we need to use the evidence to optimize the evidence lower bound to optimize to maximize the distribution of the data. So if when we have the version of the encoder model, we can learn how to reconstruct the data given the latent. The latent is the center from the prior distribution. The generative adversarial network is also called again. It's also the same thing. It learns how to generate data, but it's it's learned in different way.
in the game, we have a two kind of network with the generator and discriminator. And that generator will try to generate the image based on the Gaussian noise, on random noise. And the discriminator will try to classify the generated image and the real image. So it will be like ever training to train the discriminator to try. And so finally, uh, uh, when in the very first step of the in the very first step, the discriminator will be very easy to classify the real image and the fake image. So generator will try to generate a better image to cheat the discriminator. And after all, and after generator can generate better image, the discriminator also try to do job better. So it try to, to, uh, to classify the generated image better than it image better. So like we after very after a lot of steps we can get the finally we can get a very good generator. We can generate the image. So yeah, yeah. So diffusion model. Yeah, yeah, yeah. Right. I mean, only the conventional canon is there than the yes, totally. And there's some advances in maybe the second. Yeah, it is the same. Okay. Yeah. You want it. Yeah.
I mean, I don't have so much to say about the fusion, but we also looked at the fusion, um, where we can. So the fusion is this kind of process where you add gradually add noise to some input until it becomes full noise. So yes, usually this noise is normal distributed. We can take an image and apply in many steps apply noise to this input image, randomly distributed noise, so many times until it becomes just um, normal distributed noise. And then we can train the model to reverse this whole process because, I mean, we have the intermediate activation effect, the intermediate noise images, and we can train a model to um, reverse this diffusion process and thus, in the end, train the model to generate an image from normal distributed noise. Yes. Okay. And then finally, uh, in the final, almost final guest lecture, we also had some topic about adversarial attacks. And this lecture was mostly about how, so usually when we have a neural network, um, we usually talk about how to train it. And to train it, we do gradient descent, right? And for that, we compute the gradient with respect to the weights and do the weight update using that gradient. In this lecture on adversarial methods, we looked at how we can compute the gradient with respect to the input. So if we give it an image, if we have a network, for example, a pre-trained network, I think here it's VGGNet or something, or ResNet or whatever. And if we take this sort of network, which has in pre-training like feature extraction, whatever, and then compute the gradient with respect to the input image, we can actually modify the input image and do some interesting things with it. This we have actually seen this in. I mean, this is what we basically do in GANs, where we compute where we have the discriminator, and we compute the gradient with respect to the input of the discriminator, and then use that gradient as the in order to compute the gradient for the generator. And same can be done here. So we first looked at how we can use the gradient with respect to the input image for neural style transfer. And there they basically, in that one paper where they did that, they take an input image, quote unquote, which is just white noise, and then in many steps compute the basically optimize the input image to get, for example, representation, the network representation of they optimize from a white noise input image to reconstruct the input image from the activation in a certain layer. And that can be used to do this neural style transfer, where they apply from a certain, for example, artist, the style to a different image. And lastly, we also talked about how we can use the gradient with respect to the input image to do these adversarial perturbations. If we want to have a certain, for example, we have a classification network, and we want to find an input image that produces a certain class with a given network, then we can compute these perturbations here that if we add them onto our original image, makes the pre-trained network out with a certain class, which is not actually, even though we can see at the stop sign here, we can make the pre-trained model output something else.
Yeah, so that's the most relevant topic for the exam. We also have, basically we can ask everything we learn during the course, but mostly it will be focused on on topic we already mentioned. Yeah, so the last we will need some kind of research topic like reinforcement learning, speech synthesis, parallelism and hardwarization, and framework for deep learning, also speaker independence and handwriting, and also some traditional machine learning approach like HMM, UTP, algorithm, or Gaussian classifier. Mm, yeah. So finally, I would like to talk about the assignment, the second assignment. The task here is a part of speed tagging. Then you need to find a part of speed tagging of every word in a sentence. So it's a sequence problem. So here we will try to implement the customer architecture with the very famous framework Python. And so like the first assignment, we have a two part. First is the basic part. That means we implement the basic customer architecture, like we have the multi-head attention, we have the layer normalization, we have the feed forward layer, and we have the regional connection. And second thing is the advanced part. Here we have we can try to implement the better position embedding by using the relative position embedding. So so as you know, the positional embedding is a kind of the constant vector is a fixed value, right? So we will try to implement some learnable positional embedding, which can be considered is better. And also, we also try to design a advanced part with a space state structure sequence. And so the advanced part will be optional with the two options. Like you can choose the relative positional embedding, or you can choose the test space model. And of course, you have to do some reprocessing technique like batching. You need to group the data by many parts, and it will help the model learn faster and of course better. And the assignment is need a GPU for training, so it should be you can try it on Google Colab and submit your notebook file with Elias if you need to exercise. Yeah, I think that's all about the lecture today. So I will we are welcome every question now. Yeah, please. I think would be the end of this month, so I think it would be this week. Yeah. So yeah. And we also upload the previous exam with Elias, so you can use it for practicing. Yeah. And I think this can have some kind of similar question to the final exam in the previous exam. Okay. Yeah. The last thing that I will ask you to do give some evaluation for our course. So so you can help me by using the link. I will send you the link later, and you can give some your opinion about the course in evaluation link. And then I will update the slide. Yeah. Yeah. Okay. Thank you all, and all the best for the final exam.